Welcome students. Welcome to the today's session of ALPHORES e-learning program. So far we have studied about some applications of thermal expansions of solids, and we have to discuss one more application regarding the expansion of solids only. But let us discuss that after a little bit completion of expansion of liquids. Because of expansion of liquids, we have to consider there. So first let us go ahead with the expansion of liquids, and the next class we will discuss about an important application where we have to study by combining both expansion of solids and liquids. So presently in this class, let us start with expansions of liquids, right? When we talk about expansions of liquids, we mean thermal expansions. That means an expansion, that means a change in the dimensions as we have studied in solids because of an increase of temperature. That's why we call it as thermal expansion. But the thermal expansion of liquids is totally different from the thermal expansion of solids that we have studied so far. Then how it is different and what we are going to measure here? So let us go into the details of the topic. First of all, in the beginning of the chapter, we explained the difference between the solid state and liquid state. In solid state, all the particles are very close. Almost if you consider 1 cubic centimeter of a solid, it is expected to contain around 10 power 18 to 10 power 21 number of particles in 1 cubic centimeter. That means we can understand the solids are very close. The molecules are very close in the solid. Whereas when it is heated, let us consider ice. Let us consider a cube of ice which is in solid state. When it is heated to a temperature, automatically entire ice that will be converted into liquid state. So ice is in the solid state, and when it is heated, after the substance is coming into liquid state, that is water. So in both the cases we call it as water only, but in solid state the water itself we call it as ice. But in the conversion from ice to water, that is solid to liquid, what is basically changing is intermolecular distances. Intermolecular distances, because the distances are very small in case of solids, but now the distance are moderately increased so that the substance will be converted into liquid state. Because of increased intermolecular distances, what happens is solids are characterized by some sort of shape. The shape may be regular or irregular. It can be a regular shape or irregular shape, but there is a solid body will have a shape. That means it has fixed boundaries, fixed length, fixed breadth, fixed height or fixed shape. But liquids, when you come here, they don't have any specific shape. Whatever the container it is in which it is contained, it will have the same shape. If the container is cylindrical, the water will have the cylindrical structure. If the container is spherical, the water will have the spherical structure. Like that, whatever container is there in which liquid is present, the liquid will have the same shape. So very clearly, in case of liquid state, length, breadth, height, practically they don't have any meaning because they are not constants. For example, I will take 1 liter of a liquid. In 1 liter of a liquid, it is taken in a container like this, whose area of cross section is, let us say, 10 centimeter square. 10 centimeter square. Remember, 1 liter of volume, when you consider, it is equal to 1000 cc, 1000 cubic centimeters. So when the area of cross section is 10 centimeter square, if you say height of the liquid column, because it is a cylindrical, volume equal to area of cross section multiplied by height of the liquid column. So height of the liquid column in this case is volume is 1000 cc and it is only 10 centimeters square. So it becomes 100 centimeters of height of the water column. But now suppose I am taking the same water of 1 liter in another container having an area only 5 centimeters square. Very clearly the new height of the liquid column, it is 1000 cc by 5 centimeters square, which is around 200 centimeters. Very clearly the same volume of the liquid of 1 liter, but when you take initially in a container of cross sectional area 10 centimeters square, length of the or height of the liquid column is 100. In another container of 5 centimeters square area, the height is now 200 centimeter. Now if you study the coefficient of linear expansion, we know in case of solids we have studied the change in the length, that is L alpha delta T. Here very clearly depends upon initial length, and of course alpha, the nature of the material. Here the nature of the material may not change, but if you substitute the initial length, you will get one value. If you take another length here, you may get another value. But for a given body having a fixed dimension, delta L should be the same. But in different containers, the length of the water column or height of the water column is different. So it doesn't have a fixed length. Similarly, it doesn't have a fixed area. Therefore, because the liquids are not having a specific shape, we cannot study the linear expansion or areal expansion in case of liquids. Practically, by substituting those values for delta L and delta A, we may measure, but they do not represent the property of the material. As we said, in the case of solids, all the coefficients of expansion, alpha, beta, gamma, these are the properties of the material. That means, so for alpha of steel, if you say it is 18 to 10 power minus 6 per degree centigrade, for any body of any shape, of any size, alpha remains the same, because it is the property of the material. But now, when you are using the same liquid, alpha will be having different values, which indicate that they do not represent the property of the material, which mean that that particular value of alpha or beta or anything, they do not represent the property of the material, which mean they don't have the linear expansion or areal expansion. So that's why we do not measure the linear and areal expansions. Then what we are going to study in case of liquids? Whether you take in the first container of cross section 10 centimeters square, or you consider the second container of area 5 centimeters square, anywhere height of the liquid column is changing, but volume is remaining constant in all the containers. It is only 1000 cc, 1 liter. It is not changing. Very clearly, volume of the liquid is a constant. Because volume is remaining constant, whatever may be the shape of the container, as volume is constant, we can study the expansion of volume. So there is a clear difference in solids and liquids. So first of all, the solids, they are characterized by very small intermolecular distances, because of which they are having a specific shape. And whereas in case of liquids, because of moderately increased intermolecular distances, they don't have any specific shape, and shape of the container is the shape of the liquid column. And now coming to expansions, in case of solids we can study linear expansion, areal expansion and volume expansion. But in case of liquids, we need not consider the values of linear and areal expansions, because they do not remain constant. Length and area of cross section of a liquid column, they do not remain constant. With the container changing, they will also change. Very clearly, they do not represent the property of the material. But whatever may be the container you are taking, volume of the liquid remains constant. So hence, we can study the expansion of volume only in case of liquids. So this is one important difference between solids expansion and liquids expansion. Now coming to the volume expansion of liquids, how to measure the volume expansion? In case of solids, we have taken the volume expansion so that for a body of volume V, change in the volume delta V equal to V gamma delta T, where we called gamma as coefficient of volume expansion. Then how we have to define gamma in this case? Again, there is a difference in the volume expansion of the solids and liquids. What is that? Liquids have two types of expansion. Practically, expansion is of the same unique type, but we understand and we measure the expansion in two types. What are the two types? Let us see. I have taken a liquid in a container having a narrow neck like this, and at the bottom it is like a round bottomed flask like this. This is a round bottomed flask with a long neck like this. I am taking this type of instrument because we can clearly understand how the expansions are taking place in this container. Now, suppose the liquid I have taken initially at the room temperature, let us say T1 degrees centigrade, the liquid level is at A. So, whatever volume of the liquid is present inside the container, that let the volume is V. So, V is the initial volume at the temperature T1 degrees centigrade. Or let us say initial volume is V1. V1 is the initial volume at T1 temperature. Now, we know liquids cannot be heated directly. A solid can be heated directly. Just you put in the flame, automatically the solid body will be heated. But liquids cannot be heated directly. Liquids must be heated in a container. Therefore, when you want to increase the temperature of this liquid, first of all, we have to supply heat to the container. So, first container will get heated. From the container, heat energy is taken by the water or the liquid you have taken, and then temperature of the liquid will increase. So, directly, as we cannot heat a liquid, first of all, we are heating the container, temperature of the container is increasing, and then taking heat energy from that, the liquid is getting heated, the temperature will increase. As a result, let us suppose after the final temperature, let us say T2, final temperature is let us say T2, then final liquid level, suppose I have seen at the point C, So, C is the final level of the liquid at the temperature T2 degrees centigrade, and liquid level A, this is the level of the liquid at temperature initial T1 degrees centigrade. Very clearly, from T1 to T2, when the temperature is increasing, there is an increase in the liquid level from A to C. If you say A is the area of cross section of this cylindrical tube present here, for the long neck, area of cross section is uniform and it is A. Then change in the volume of the liquid, delta V. If you consider liquid level is changing from A to C it is changing. So the change in the volume is change in the height of the liquid column, that is A to C multiplied by area of cross section. So this is the change in the volume. Therefore, the change in the volume, because it depends upon the initial volume, we can say that delta V equal to V gamma delta T. Otherwise, if you take the coefficient of expansion, gamma equal to change in the volume divided by initial volume into change in the temperature. Just as in the case of solids, we can define the value of gamma. So gamma is change in the volume divided by initial volume and the change in temperature. From this equation we can find out the value of gamma. So now we got the coefficient of volume expansion of the liquid. Now we have to understand one important point. First of all, initially liquid level is at A, and finally when the temperature is increased from T1 to T2, liquid is expanding up to C. Then we said AC corresponds to expansion of the liquid, and change in the volume of the liquid is delta V, is the product of the change in the liquid level AC and the area of cross section. And from that change in the volume, we are defining the gamma like this, where V is the initial volume, delta V is the change in the volume. Now in this equation, let us say delta V is AC multiplied by area of cross section, and V is the initial volume into delta T. Now this is known as what is called coefficient of apparent expansion. When we are going to study about the volume expansion of the liquids, as I told you, there are two types of expansion. Two types in the sense we will study them or we understand them in two ways. Here we have seen the liquid level initially at A and finally the liquid level appears at C, so that apparent change in the volume, apparent in the sense what actually it appears there, what is actually appearing there for the expansion is from A to C. So A to C, this delta V change in the volume is called apparent change in the volume. So apparent change in the volume, taking the delta V, this coefficient is called coefficient of apparent expansion. Coefficient of apparent expansion. Now let us understand the phenomena a little bit more deeply. What do you mean by that? What do we mean? For practically, when you are increasing the temperature of this liquid, let us say from T1 to T2, we said liquid is expanding from A to C. But before the temperature of the liquid is increased, we know the temperature of the container is increased. We are directly heating the container only. We are not heating the liquid. So from the container, heat energy is taken by the liquid, then liquid is expanding. So before the expansion of the liquid is taking place, we are increasing the temperature of the container, so container will expand. The expansion of the container will also be there. So to make it convenient for us to study the expansion, let us suppose that first of all the temperature of the container is increasing from T1 to T2. It is only to understand it conveniently. What we are doing is practically both the expansion of container and expansion of liquid, they are simultaneously taking place. But only to make it convenient for us to understand, let us suppose initially the temperature of the container is increased from T1 to T2. After that the liquid is taking heat energy and the temperature of the liquid is increasing from T1 to T2 and liquid is also expanding. But prior to that, the temperature of the container is increased from T1 to T2. We know because the container is made up of a solid, depending upon the nature of that material, definitely there will be an increase in the volume. When the volume of the container is increased, you can say it becomes a slightly bigger container. You can say that it is a slightly bigger container because volume is increased now. Suppose when the same liquid is placed in a smaller container and bigger container, we can understand, we have taken in the previous example, when the volume of, when the cross section of the container is 10 centimeter square, liquid level is 100. But for the same 1 liter of volume that we have discussed previously, for 5 centimeter cross section of area of the container, liquid level is changed to 200. So when the volume, when the container is changing, the area of cross section or volume, liquid level also changes. So practically what is happening, because of increase of temperature, as the container is expanding, automatically it is a bigger container. Automatically to keep the volume of the liquid as a constant, because liquid is not expanding so far, only container is expanding. As a result, because of the constant volume of liquid and container is expanding to be a bigger size, the liquid level should fall. So practically the liquid level is falling from C to, let us say, B. C to B, it is decreasing. Practically volume of the liquid is not changing, but container is expanding. So it becomes a slightly bigger container. So because the container is a little bit bigger, the level of the liquid will decrease. Then liquid level is falling from A to B, and then because of increase of temperature of the liquid is increasing from B to C. So the actual expansion of the liquid is taking place from B to C, not from A to C. Practically when you measure the liquid level, initially it is at A and finally at the higher temperature liquid level is at C, it is true. But it is only for appearance, initially it appears at A and finally it appears at C, so that the apparent change in the volume corresponds to AC only. So corresponding to this apparent change in the volume, we call this as coefficient of apparent expansion. But practically it is not the actual expansion of the liquid. liquid level practically it is decreasing a little bit, coming down from A to B because of expansion of the container, and then liquid is expanding from B to C. So the real expansion of the liquid is from B to C. Therefore you can define another coefficient taking the real change in the volume. This delta V from A to C here is only an apparent change in the volume, but if you consider the real change in the volume from B to C, we define another coefficient called coefficient of real expansion. So coefficient of real expansion, how we measure? It is the change in the volume, but we take the real change in the volume. So delta V, which is real, divided by initial volume into change in the temperature. Basic definition is not changing. Basic definition is the same. But if you take apparent change in the volume, that is from A to C, you will get coefficient of apparent expansion. But if you take real change in the volume, that is from B to C, you can calculate coefficient of real expansion. So like this, in case of liquids, because of involvement of expansion of the container, try to understand the statement. I am repeating. Because of involvement of expansion of the container. So always the expansion of a liquid is always associated with the expansion of the container. That's why if you consider the expansion of the container, liquid level is falling and then it is increasing from B to C, then we are calculating coefficient of real expansion. But if you do not consider the expansion of the container, simply initial liquid level is at A and final liquid level at higher temperature T2 is C. So AC corresponds to change in the volume, that is apparent change in the volume. So when we consider apparent change in the volume or apparent expansion coefficient, we do not consider expansion of the container. Simply we take what is the initial level, what is the final level, depending on that we can find out coefficient of apparent expansion. But when we want to study about the real expansion of the liquid or coefficient of real expansion of the liquid, you must consider expansion of the container. When you consider the expansion of the container, liquid level will fall from A to B. Then it will be increasing from B to C, so that the actual expansion, real expansion corresponds to BC. Therefore, we can say that gamma A, gamma R, here it is BC is the real expansion multiplied by area of cross section, that is the change in the volume, by V into delta T, you will get the coefficient of real expansion. So here one important thing we have to remember is, when you are studying about coefficient of apparent expansion, we are not considering expansion of the container. Simply we take initial level and final level, that's all. But when you want to talk about the real expansion, actual expansion of the liquid, then we have to consider the expansion of the container, so that liquid level will fall from A to B and then it will expand from B to C. So BC corresponds to the real expansion of the liquid. So when we talk about apparent expansion, we do not consider the expansion of the container. But when we talk about the real expansion, definitely we have to consider the expansion of the container. So these are the two types of coefficient of apparent expansions. But in general, we can take a value or we can give a general relation, gamma equal to delta V by V into delta T. If delta V is the apparent change in the volume, this represents coefficient of apparent expansion. If delta V is the real change in the volume, this represents the real change in the coefficient of real expansion of the container, of the liquid, right? So there are two types of coefficients of expansion for a liquid, even though it is having only volume expansion. So it is a coefficient of apparent expansion if this is a coefficient, apparent change in the volume. If this is a real change in the volume, the same equation you will get the coefficient of real expansion. So there are two types of expansions in case of liquids. Now let us have a relation between these two. Then how to get the relation between these two? Now let us take the liquid levels like this. Here liquid level, it is falling from A to B and then it is increasing from B to C. So here what we have to understand is A to B, the liquid level is decreasing. Why the liquid level is decreasing? Liquid level is decreasing because container is expanding. Container is expanding. It is becoming a slightly bigger container. So whatever change in the volume, change here taking place, because the liquid level when it is falling from A to B, it appears as if the volume of the liquid is decreasing here. But practically volume of the liquid is same. But because the container is expanding by equal amount, the volume of the liquid appears to decrease. I hope you understand. Whatever change in the volume of the container is taking place, that is the same amount of change appears to be taking place in the liquid also, so that the liquid volume appears to decrease from A to B. So the change in the volume of the liquid from A to B, that indicates the change in the volume of the container. So AB corresponds to expansion of the container. Expansion of container. Now A to C, if you consider, AC corresponds to, A is the initial level of the liquid, C is the final level of the liquid, then AC corresponds to what is called apparent expansion of the liquid. This is the apparent expansion. And now actual expansion is from B to C. So BC corresponds to the real expansion of the liquid. So AB corresponds to expansion of the container because liquid level is falling, so that the change in the volume of the liquid, that is from A to B, is equal to change in the volume of the container. So AB represents expansion of the container, A to C that represents apparent expansion of the liquid, and from B to C we can say it is the real expansion. Very clearly from the diagram what we can see here, we can write that BC equal to, we can say AC plus AB. BC is equal to AC plus AB. Then how to get the values of BC? Previously we have defined that coefficient of real expansion, that is real change in the volume. So it is BC multiplied by area of cross section divided by initial volume into delta T. And coefficient of apparent expansion, this is the apparent change in the volume is from A to C. So it is AC multiplied by area of cross section by V into delta T. For the container also, change in the coefficient of expansion of the container, let us say gamma of the container or gamma of the solid, that is change in the volume is from A to B. So change in volume is AB multiplied by area of cross section divided by initial volume into change in temperature. Now from these values of gamma or gamma A and gamma of the solid, let us take the values of BC, AC and AB and substitute. What we will get finally? When we substitute here, I may remove the diagram here. If you substitute all these values, let us substitute here. What is BC? So BC very clearly it is gamma R into V into delta T by A, that equal to AC. From this equation, AC is nothing but gamma apparent plus volume into delta T divided by the area of cross section plus AB. AB corresponds to the expansion of the container. So from this equation, AB is gamma of the solid V into delta T divided by A. So when other factors which are common on both sides are removed, the final equation we will be getting is gamma R equal to coefficient of apparent expansion gamma A plus gamma S. This relation is an important relation which gives the relation between coefficient of real expansion and coefficient of apparent expansion. So gamma R equal to gamma A plus gamma S. This is the volume expansion of the container, this is the volume apparent expansion of the liquid, and this is the real expansion of the liquid. Now after knowing this relation, gamma R equal to gamma A plus gamma S. Very clearly gamma R, it is the actual property of the liquid. Whatever may be the container, gamma R always remains constant because it is the actual property. Whereas apparent expansion represents only the expansion of the container, expansion of the liquid with respect to that particular container. I repeat, real expansion, coefficient of real expansion represents the absolute property of the liquid, the true property of the liquid. Whereas gamma A or apparent expansion represents only the relative property of the liquid with respect to the container. Because gamma R is a constant for a given liquid, but depending upon the gamma of the container, gamma A will be changing. Gamma A will be changing. In different containers, gamma A will have different value. If gamma S changes, gamma A also changes. So gamma R is the property of the liquid which remains constant in all containers, because it is the absolute property of the liquid. But gamma A, it is the relative property with respect to the container. So in different containers, as the gamma S changes, gamma A also changes. So try to remember that gamma A apparent expansion, coefficient of apparent expansion is the relative property of the liquid with respect to container, and the absolute property of the liquid is coefficient of real expansion. So this is the general relation, and this we can also write like coefficient of real expansion is gamma A plus gamma S. What is this gamma S? Is coefficient of volume expansion of the container. When the container is made up of an isotropic solid, this gamma we can write as 3 alpha. So we can also write like 3 of alpha S. So this relation is also useful in solving the numericals. So these are the relations between coefficient of real expansion and apparent expansion of a liquid. Now let us discuss the consequences of the real and apparent expansions of a container depending on the values of gamma A and gamma R. Gamma R is generally, we said, gamma A plus gamma of the solid or gamma of the container. Suppose in the example we have taken previously, the liquid level initially it is at some A, and the liquid level is falling to B, and then it is increasing to C. So we said BC is the real expansion and AB is the apparent expansion. So in this case, in a container like this, container is also expanding here. Container is also expanding. Because of that only liquid level is falling from A to B, and finally from B to C it is expanding. But it appears to be expanding only from A to C, which is the apparent expansion. Now in a container like this, suppose I have taken a liquid, I am increasing the temperature. What is happening to the liquid level? Liquid level is continuously increasing. Liquid level is continuously increasing, and in this case coefficient of real expansion is greater than coefficient of apparent expansion. Now let us consider a case where there is a possibility that there is a container made up of a material which contracts on heating. There are certain metals. The best example is type metal. Type metal is a metal which contracts on heating. So if the container is made up of such a material which contracts on heating, what happens is initially liquid level is at A, but now when you are increasing the temperature, instead of expanding, liquid is contracting. The container is contracting. When the container contracts, we can consider that it becomes a slightly smaller container. Then automatically liquid level will rise. Liquid level will rise without changing the volume of the liquid itself. Only because the container is contracting, liquid level is increasing. And after that, when the liquid is temperature of the liquid is increasing, again the liquid level will increase from B to C. So what is happening? Initially liquid level is at A, and finally liquid level is at C. So AC corresponds to the apparent expansion. But practically what happened? Because the container is contracting, as the temperature of the container is increased, the liquid level is increased from A to B without increasing the volume of the liquid. In this process, when the liquid level is increasing from A to B, Liquid is not expanding, only container is contracting. As a container is contracting, because it is becoming a small, little bit smaller container, liquid level is rising from A to B, and then from B to C, the liquid level is again rising. So liquid level is rising from B to C because of real expansion, but practically it appears to be increasing from A to C. So AC corresponds to the apparent expansion, and BC corresponds to the real expansion. Very clearly from the diagram we can say apparent expansion is more. Apparent expansion is more because coefficient of expansion of the container is negative. In such a case we can say gamma R plus gamma S equal to gamma A. Because this is becoming negative, then it becomes gamma R plus gamma S is gamma A. That is, coefficient of apparent expansion is more than coefficient of real expansion. Only this is possible in a container which contracts on heating. Because the liquid level is increasing without increasing the volume of the liquid. Only because of contraction of the container, the expansion appears to be very large. So in general, in any container which expands on heating, this equation will be as it is. Liquid level will be rising little bit slowly. But in a case where the container is made up of a material which contracts on heating, this is the suitable equation, and very clearly liquid level will be rising very fast. Then coefficient of apparent expansion is larger than coefficient of real expansion. And there is one more possibility that as per this equation, suppose I take a container which will not contract or which will not expand. That means volume of the container remains as a constant at all temperatures. That means the coefficient of expansion is negligibly 0. In such cases, because the container is not expanding or not contracting, gamma S is 0 or gamma R equal to gamma A. That means the coefficient of apparent expansion and real expansion, both of them are equal. But in this case also, liquid level continuously rises. Liquid level definitely continuously rises. But liquid level will be increasing slowly than the previous case where the container is contracting. So when in the container where the liquid level will contract, container is contracting, the liquid level increases very fast. And here liquid level will be rising very slowly, but practically we cannot determine any change in the liquid because apparent expansion and real expansion are equal. So as the solid is not expanding, whatever expansion is taking place, it is only because of real expansion, and because apparent and real are equal, in this condition liquid level will always be, suppose initial liquid level is at A and finally it will be at B. This is the real expansion and this is also the apparent expansion, because there is no involvement in the expansion of this container. Container is not expanding, so there is no involvement of expansion of the container. So apparent expansion, real expansion, both of them will be equal. So this is one more possible case. So these are the relations required present between the two types of expansions. So with this, let us stop in our class. In the next class, we will go to some more details and other applications of this particular topic. And another application that we have studied, that I have told you about, the combined application in solids and liquids also, we will discuss in the next class. So with this, let us stop here. We will continue next class. Thank you very much.